Okay, so this is the first lecture in a 5 to 6 lecture course on ring theory. Fine. And our main focus will be commutative ring theory, rather commutative rings with unity. In fact, this course can be thought of as an entry-level course. So this can be thought of as an entry-level course in field theory. Our main focus will be to develop the ring theory in order to be efficient in studying field theory. Okay. In fact, if you want to study module theory, in that case as well, this will be you can consider this to be a very important sort of a course, and I'll try to keep it within 5 lectures. At most you can reach 6 lectures, but I'll still try to keep it within 5 lectures, and this will be as detailed as possible. And most of our discussions will be regarding polynomials, but we'll try to give as much possible concepts regarding ring theory in any ordinary ring theory course. Okay, this won't be a a very surface level course. It will be a detailed course, a very detailed course, but in most of the cases where we can, we'll try introducing notions of polynomials. And in this course, I'll assume that you are all at most a little familiar with, rings. Okay, we're not going to get into very detailed introduction to rings. Okay, I'll just give the definition in order to set up a completeness because of the first lecture, but I'll assume that you know at least what a ring looks like. Fine. Okay, so yeah, so if I talk about a simple prerequisites, so the only thing which we require is a good course in group theory. I'm talking about a good course, not a very important course, but just a simple course in group theory, which includes the notions of groups, subgroups, normal subgroups, quotient groups, homomorphisms, isomorphisms, so on and so forth. Fine. And just the surface level rings. Okay, I just guess you guys know what a ring is. Simply that. Fine, nothing else. Okay, yeah. So let's start with the discussion of rings. And firstly, in some sense, I can tell you that this ring, any ring, the notion of rings has developed up from the idea of generalizing integers. Generalizing the operations defined on integers, generalizing the properties of integers. Okay, in some sense you can think it to be like that. Okay, fine. Now, so let us start with the definition of rings. Fine. Okay, our main focus will be commutative rings with unity, as I said. So a commutative, this will be our symbol, a CRUR. That means a commutative ring with unity is a set R, which is an additive abelian group. Okay, so we already have R to be an additive abelian group, and a binary operation, which we define as dot. So additive abelian group, fine, dot, such that property number 1 is that A dot B dot C is same as A dot B dot C for all ABC in R, and secondly, A dot B is equals to B dot A for every element in R, and number 3 is that there exists an element which we denote as 1. You can simply talk about 1 to be a symbol. Do not attach any known meaning to either the term additive or the operation, which I am constantly saying to be a multiplication or a dot. And in fact, the symbol 1, don't attach any meaning, any numeric meaning to any of these right now. We'll see why have we used these symbols. As I just said, that everything is thought of to be a generalization of the integers, and therefore these symbols make sense, but do not attach any meaning to it, because in certain scenarios we'll keep alternating the meanings of these operations. Fine. So there exists an element 1 in R, such that any number multiplied or operated with 1 using the dot operation will give back the element itself. Fine. In that case, what we say is that R is a commutative ring with unity, and an extra operation is required, which sort of relates the two binary operations which we have, the addition and the multiplication. Is that for every element A, B, C in R, A dot B plus C is same as A dot B plus A dot C, which is called the left distribution, and A plus B dot C is equals to A dot C plus B dot C, which is called the right distribution. Fine. Okay. Now just let me tell you something here, that if only the first condition is satisfied and the fourth condition is satisfied, the fourth condition is always necessary to be satisfied. If in addition to the fourth condition, the first condition is satisfied, then we can say that R plus dot is just a ring. Okay. If in addition to 4 and 1, 2 is satisfied, then we say R to be a commutative ring. Okay. And if 3 satisfies as well, then obviously we have already defined it to be a commutative ring with unity. Fine. Okay. Now there is a certain terminology related to saying that we denote the ring to be a triplet. Okay, so we have the set, we have the plus operation with respect to which R is an additive abelian group, and we have this new binary operation, and so this is called a ring, or rather a notation for rings. Okay, and this R plus, this does the duplet R plus, this is called the abelian group. This is called the abelian group obtained from the ring. Or a more technical term is often used, induced from the ring. Okay, fine. Now after this, whatever discussion we do, every discussion will be related to commutative rings with unity. Even in some case I write the notion of a ring, I mean a commutative ring with unity. Fine. Examples. Easily, this is a very easy check for you guys who are seeing this lecture, that the ring of integers, the ring of real numbers, the ring of rationals, the complexes, all form commutative rings with unity with respect to usual operations. Usual operations mean whatever addition you know, whatever multiplication you know, and whatever usual meaning you can attach to the element 1. Fine. Very easy to observe. The next example is actually somewhat a non-trivial example, but if you study groups, you also know this example. That is the collection Zn, okay, which consists of the equivalence classes of the modular arithmetic divided with or rather I should say, you can think of the modular arithmetic. Basically, let me say it in this way. Okay, given A in R, we can always define a division in R, or rather let's say Z. We can always define a division in Z, right? We can try and define a division in Z. So we can write A as Qn plus R, okay, usual Euclidean algorithm, and in modular arithmetic we say this implies that A is congruent to R mod n. Fine. And we furthermore what we know is that this R is greater than or equal to 0 and less than n. Fine. What we do is that, so there are basically how many possibilities? There are n minus n possibilities, right? So R can be anything from the set 0, 1, 2 till n minus 1. So what we do is that relate any two elements which have the same remainder. Okay, relate any two elements which have the same remainder, then the remainder will fall into one of these elements and take the collection of all those elements as a single class. Fine. So I can define Zn to be the class of 0, the class of 1, the class of 2, and so on till the class of n minus 1, sorry, where we can think it to be in this way, that this class is the collection of all those elements, or rather let me write it in a more general way. So the class of the element I denotes the collection of all those elements in Z such that X is congruent to I mod n. Fine. We can obviously do this because there are only a finite possibilities for all these integers, for the remainders of all these integers, right? So this is usually defined as a Zn, right? Something which we already know. So this Zn, in fact, forms a ring, a commutative ring with unity. This is a commutative ring with unity with the operations as, so A plus B is defined to be A plus B modulo n. Okay, so it's defined as A plus B modulo n, and the multiplication is defined as A times B modulo n. Fine. Let us solve as an example. Okay. And for simplicity, I'm telling, for simplicity, whenever I will be writing this set Zn, I won't be writing them as classes, or we will simply write them as numbers from 0 to n minus 1. Okay. Fine. So, example, what is Z6? So Z6 should be the collection of these numbers 0, 1, 2, 3, 4, and 5. Right? Choose any two numbers from here. Let's say, choose the number 2 and 3 from Z6. Then 2 plus 3 is 5, or rather, let me choose a larger number, then you will be better understanding. Choose 4 and 5 from Z6. Then 4 plus 5 is equals to 9. Mod 6, that is something which we need to do. So this should be exactly equal to 3, right? Okay. Similarly, 4 times 5 is 20. Mod 6, right? This should be equal to 2. Therefore, 4 plus 5 is 3 in Z6 and 4 times 5 is 2 in Z6. Got it? Okay. Fine. So this, the other term for this ring is the congruence modulo n ring. Okay. Congruence class of n. There are multiple terms to talk about. Fine. Got it. Okay. The other important example is the following. Okay. Let R be a ring and define the symbol x. How do we define the symbol x? We define the symbol x as the following. Okay, x as 0, 1, 0, 0 and continue. So this is called an infinite sequence. This is called an infinite sequence from the elements in R. Okay, clear? Okay. Now define or let C1, C2, C3 and so on, and D1, D2, D3 and so on be sequences in R. Okay. So what we are basically doing is that we are choosing arbitrary elements from R and we are making an infinite ordered pair. You can think of it in that way. Okay. Now set the following operations. I think you have never seen such an introduction to polynomials, so it is a good thing to know. Set the following operations. So C1, C2, C3 and so on plus D1, D2, D3 and so on can be written as C1 plus D1, C2 plus D2, C3 plus D3 and so on. Clear? Okay. So what we are doing is basically component wise addition. The multiplication will be defined slightly differently. So let me do it in the next page. Define C1, C2, C3 and so on plus D1, D2, D3 and so on as the collection E1, E2, E3 and so on, where E1 is equal to C1 D1, E2 is equals to C1 D2 plus D1 C2. Fine. Okay, it will be better to not use the indices C1, or rather we slightly modify the things. Okay, let me make a slight change. Okay, we'll surely understand why we are making this change. Wait a second, just wait a second. Fine. Okay. Yeah, I know it is bothering you a lot, but still fine. Okay. So let me define this to be C0, C1, C2, D0, D1, D2. So C0, C1, C2, D0, D1, D2. So this is C0 plus D0, C1 plus D1, C2 plus D2. And here also have C0, C1, C2, D0, D1, D2. Here we have E0, E1, E2. So E0 is basically C0 times D0. E1 is basically C0 D1 plus D0 C1. E2 is basically C0 D2 plus C1 D1 plus C2 D0. So and so on. En will be Ci Dj such that I plus j is equals to n. Fine. Okay. Now define f of x to be the ordered pair C0, C1 till Cn, and all of the other elements in the sequence just make it 0. Okay. So this will be our definition of a polynomial in this case, and we'll see why. Okay. So this corresponds to our usual polynomials over R in a single variable. Okay, in a single variable. How is it so? Let us just observe it. It's a very simple check. See, we are defining x to be this, right? And if the other element is 0, fine. So you can observe that x0 is 0, 1, 0, so on, times 0, 1, 0, and so on. So the first element should be 0. The second element should be 0 times 1 plus 1 times 0, so 0. The third element should be 0 times 0, right? So it should be first element times the second element, yeah, so it should be 1, right, and so on, right? And you can continue this, in fact, okay? So basically, xi will be the element which having 0 everywhere and 1 in the ith spot, okay? Or rather, 1 in the I plus 1 spot. If you consider this to be the, okay, consider the first element to be the 0th spot, so it will be in the ith spot. Fine. In that case, observe what is your f of x. So your f of x is, how we defined it to be c0, c1 till cn, and all the rest of the elements are 0. So this should be c0, right? All the elements are 0 plus 0, c1, 0, and all the elements of 0, continuing till cn, this should be 0 till cn, 0, and all the elements are 0 again, continues. So we can definitely write this as c0 times the element 1, 0, and so on, plus c1 times the element 0, 1, 0, and so on, right? Plus c2 times the element 0, 0, 1, and so on, till we get cn times the element 0, 0 till 1 in the nth spot. All the other elements are 0, and we don't get anything. Other elements will simply correspond to the zeros, right? Nothing else. Fine. So you can observe that this will correspond to simply 1 if you observe carefully with the usual definitions of addition and multiplication which we have defined. So this becomes c0 plus c1x plus c2x square and so on till cn x to the power n. And that's it. That is your standard polynomials. Okay. Having this in mind, we can no more talk about defining polynomials in this coordinate fashion. In fact, we can define Rx to be the collection of elements of the form a0 plus a1x and so on till an x to the power n, such that each ai comes from R and x is a variable, simply a symbol, which depends on the scenario in which we are talking. Fine? Okay. Now we can observe that we have already a well-defined operations in the case of these polynomials. In simple words, the operations in Rx are component-wise addition. That is, if you have summation ai x to the power I plus summation bj x to the power j, then if you want to add them, you just add ai plus bi x to the power I in this way. So a0 gets added to b0, a1 gets added to b1, and you get a resulting polynomial. Fine. The multiplication is somewhat different. In case of the multiplication, what you have, so the multiplication in case of polynomials is what we say to be a Cauchy product. Okay. So the multiplication, so it is defined to be the Cauchy product. So if you have, say, fx equal to a0 plus a1x plus a2x square and so on till an x to the power n, let us consider both the polynomials with having the same highest degree of x. Okay. So let's say to b0 plus b1x plus b2x square and so on to be bn x to the power n. Then fx times gx is the polynomial a0 b0 plus a1 b0 plus a0 b1x plus a0 b2 plus a1 b1 plus a2 b0 x square, so on and so forth. This should be the collection of all the coefficients in this way, so that I plus j adds up to n, and this is x to the power n. Okay. So these coefficients are basically called the Cauchy coefficients. Clear? Okay. So now, as the usual meaning you have of polynomials, and we won't need to consider this coordinate way of introducing polynomials anymore. Okay. Now, given a polynomial fx in Rx such that f of x is a0 plus a1x and so on to be an xn, it's a very useful assumption that an is non-zero. Okay. Why? Because once we choose so this is called the leading coefficient. Okay. This an is called the leading coefficient. Once we set the leading coefficient to be non-zero, we can define the degree of f. The symbol I will be using is del f, is defined to be the highest power of x present in the polynomial. Fine. Okay. If this an is 1, then we say fx is monic. Fine. Okay. a0, which can be thought of as f when x is equal to 0. Once we said x is equal to 0, go for the normal operations. Okay. Having in mind, this I should have mentioned previously, but it's not till late, that in any ring, we assume that x times 0 is same as 0 times x is equal to 0 for every x. Okay. Fine. So you multiply 0 with any element, you get 0. So you can think of as just setting x equal to 0, then this is called the constant term of f. Fine. So 0 just corresponds to, let me just, you can think of it to be 0 as the 0 polynomial. It just corresponds to the infinite sequence zeros everywhere. Fine. Okay. Now, depending on the degree of a polynomial, we have what we call a linear polynomial if the degree is 1, we have a quadratic polynomial if the degree is 3, cubic if degree 4, cubic if degree 3, quadratic if degree 4, and quintic if degree 5. Fine. An important definition: let fx be an element in Rx such that f of x is equals to summation ai x to the power I I ranging from 1 to n. I not often write where how I ranges, sorry, I ranges from 0 to n. Okay, you can just think of the summation to be always from 0 to n, unless specified. Okay, then we say that alpha in R is a root of f, or often we say that f admits a root alpha in R if f of alpha, which is summation ai alpha to the power I is equals to 0 to n, is exactly equal to 0. Fine. Example number 1, let f of x be x square minus 2x plus 1. So this is a polynomial over zx. Okay, then observe that f of 1, or rather observe that f of x is just x minus 1 whole squared. Since this is commutative, you can just verify that it is exactly the thing, because you can just split x minus 1 whole squared into x minus 1 into x minus 1 and just distribute. Okay, just distribute. You can in fact observe that the Cauchy product, the way we have defined the multiplication in case of polynomials, it is just the simple distribution, nothing else. Okay, distribution in terms of polynomials and then grouping them according to the degrees, nothing else. Okay, for example, I hadn't write it right. So this is just, see, I'm taking a small example. So suppose I have a0 plus a1x times b0 plus b1x. So this will give me a0 b0 if I just distribute, plus a1 b0x plus then what should I get? a0 b1x plus a1 b1x square. So just group these two terms, keeping this identifier x. That is the way we have defined this Cauchy product. So it's simple distribution, nothing else. Fine, let's go back. So this is just this, and this you can easily observe that f of 1 is 0. Fine. So f admits a solution, or rather f admits a root over z. Number 2, let f of x be x square minus 2, and consider this to be a polynomial over qx. I mean over q. You could also have considered this to be a polynomial over z, because the coefficients are each coming from z. Observe that the only root f admits is root 2. Okay, plus or minus root 2. Anything independent of sign is root 2, and it's irrational, you know, from basic number system. And irrational number, so therefore root 2 is neither in q and in fact so not in z. So therefore f, though it admits a root, it doesn't admit a root in the ring specified to us. Okay, and this can happen in any case, that you are given a polynomial over a certain ring, though the polynomial seems to have a root, the root does not belong to the ring specified. In that case, so this is also a definition, if f is a polynomial of degree 2 or 3 over some ring R, we say f is irreducible. We will have a stronger notion of irreducibility later. We say f is irreducible over R if there does not exist some alpha in R such that f of alpha is 0. Okay, and this definition is applied only for degree 2 or degree 3 polynomials. Okay, given a ring, we say that it is irreducible over that ring if it does not have any element in that ring which gets evaluated to 0 under f. Fine. Okay, but you can easily observe that this f, you can also treat this to be a polynomial over Rx. I mean in Rx. R is the real ring. Okay, in that case you will see that f admits a root, because root 2 is a real number. Getting my point? Fine. Okay, fine. Now there is a certain level of symmetries, or rather what we call symmetric functions, associated to polynomials. Symmetric functions associated to polynomials, what are they? Suppose alpha 1, alpha 2 till alpha n are all the roots of some polynomial. Let me not specify any ring. It will hold for any ring. Okay? For some polynomial f, then, or rather, let me not talk about it simply in terms of roots. We will be attaching these notions later. Let f of x be this polynomial, x minus alpha 1, x minus alpha 2, so on and so forth till x minus alpha n. Fine. Then you can see alpha 1, alpha 2 and alpha n are all the roots of f. Okay. There can be more roots because we are not specifying any properties of these alphas, but for now we are simply defining this to be this. Okay. Fine. And if I write this as summation ai x to the power I is equals to 1 to n, 0 to n, then what you can do is that using induction, you can take this to be an exercise. Using induction, we can see that your Cn should be 1. Fine. Your Cn minus 1 should be the negative of the summation of all these roots alpha 1 I. Okay. Cn minus 2 will be the positive sum of the roots as alpha I, alpha j, where I is less than j, and you can continue doing this till you get C0 to be the minus 1 to the power n summation. So no summation required here. It's just the product of all these roots. Okay. Fine. Okay. Fine. So these are called the symmetric functions, associated symmetric functions. Okay. So observe that the problem of finding the roots. So why did I write this? The problem of finding the roots of f of x, because we can see that alpha 1 to alpha n are all the roots, right? In fact, if you attach the property that alpha I is not equal to alpha j for all I not equal to j, then these are all possible roots of fx. You can easily observe that, right? You cannot have any other root of fx, fine, provided any field. So the problem of finding the roots, in fact, if alpha 1 is not, if we do not attach this notion, alpha I might equal to alpha j for some I not equal to j, in that case also you can see, but there the number of roots will be reduced from n. Here we have n roots, or as written itself as n roots. You can have a smaller number of roots if you say that two distinct alpha i's can be same. But still, it is not the matter of fact which we are concerned about. What I'm concerned about is that to find the rule, that is to find these alpha I, alpha j, what we need to do is we need to solve this collection of equations, this set of equations. So the problem of finding the roots of fx, alpha 1 till alpha n, from its coefficients, because if we are given a polynomial, we will obviously be given its coefficients. From its coefficients is solving a non-linear, and this is obviously not a linear system, so it's a non-linear system of n equations in unknowns, right? So this is called solvability by radicals. This is called, or rather this notion is called solvability by radicals. And we will later show that polynomials of degree greater than or equal to 5 are not solvable by radicals. If a certain polynomial is solvable by radicals, then you will get a general formula to find the roots of those polynomials. For example, if you have this famous Sridhar method to find any root of, or rather to find all the roots of a quadratic polynomial, quadratic equation, in fact, you can think of it to be like in that way. So because quadratic equations are solvable by radicals, so any equation which is solvable by radicals will give you a general formula to calculate the roots, which is not possible for quintic polynomials or higher degree. Fine? Okay. Now these are some elementary properties of rings. Some elementary properties of rings which you can verify. Number 1 is that the element 1 in R is unique. Number 2, 0 times R is equal to 0 for every R. Now we had given this to be a definition, but you can in fact prove this. And number 3 is that minus R can be written as minus 1 times R for every R. Yeah, the proofs are quite elementary. See, why is it true? Suppose you have another such element. Okay, suppose you have another such element. Let's say E is in R is another 1. Okay, distinct from 1. Then what we have is that E times 1 is equal to E, because 1 satisfies this property, and E times 1 will also be equal to 1 because E satisfies the property, right? 1 is an element of R, E is an element of R. That is why we have this. So we must have equal to 1. In case of 2, you can prove it in this way. What is 0 times R? So you can write 0 times R, or rather you can write 0 times R as 0 plus 0 times R distributed. So you get 0 times R plus 0 times R. So these two get cancelled out. So you get 0 times R is equal to 0. Fine. The third property is also very easy to prove. Observe that I can write 0 as 0 times R, which can be written as minus 1 plus 1 times R, which can be written as minus 1 times R plus R. So if you send R on the left hand side, you get minus R, or if you add with minus R on both sides from the right, you will get minus R to be minus 1 times R. In the same way, you can prove the fourth property rather, that is minus 1 times minus R is R. Okay, for every R. Okay, take this to be an exercise. Clear? Okay. Now let us move on. Okay. Fine. Clear? Now this is something important to observe. We never want 1 to be equal to 0 in any ring R except the trivial ring which consists of only the 0 element. Now you know that this is a trivial additive group, and if you consider a multiplicative operation on it, then you can define it to be just 0 times 0 equal to 0. That is the only element in which 1 by definition is equal to 0, and we don't allow 1 to be equal to 0 in any other ring. Okay, fine. Okay. Now there is an important observation. One second. Right. Now here you will observe an important thing, that why division by 0 is not allowed. Okay, why division by 0 is not allowed. To have that, we need just a simple definition of a unit. Okay, so A in R is a commutative ring with unity, is said to be a unit. If there exists some, okay, so this is a non-zero element. If there is an element, or rather, let me say it in this way. Let us not attach any notions of 0 or non-zero. If there exists some element B in R such that AB is equals to 1 is equals to BA. Fine. In that case, we say that B is equal to A inverse, and this is called the inverse of A. Fine. Now observe that if I have AB inverse and I multiply it with B, due to commutativity, I get it to be A. No problem in that. Clear? Because if I commute these two, I get B inverse A. I can associate B and B inverse, I'll get 1 times A is A. Now suppose division by 0 is allowed. Okay. Then in R, CRU, there is some element of the form 1, or rather, 1 by 0. See, we often write A inverse as A by B, conventionally regarding the notions of integers. So in R, 1 by 0 times 0 should be 1, right, from here, right? But since we are multiplying this element by 0, this should be 0 by definition, right? Let me write it clearly. So suppose division by 0 is allowed in R, then 1 by 0 multiplied by 0 should be 1 from here. But 1 by 0 should be an element of R itself, because 1 is an element of R, and 1 by 0 is nothing but 1 times 0 inverse. Since 0 is in R, 0 inverse should be in R by the definition of this unit. We are regarding 0 to be a unit, nothing else. So this element is in R, 0 is in R, so 0 times this should be in R, and this should be equal to 0 by the definition of multiplication by 0. So what we conclude is 0 is equal to R, which is forbidden, right? We just said that this is forbidden in any definition of ring. That is the reason why division by 0 is not allowed. In fact, 0 can never be a unit. As for all, or rather, because if you multiply, when it is said to be a unit, if you multiply any element, if you choose an element, it is said to be a unit. If there exists another element which when multiplied gives you 1, but if you multiply any element to 0, you will get 0. You will never get 1. So you can never treat 0 to be a unit, and you can never allow division by 0, or rather, you can the other way of telling it, you can never allow the notion of the inverse of 0. Okay, you need to keep this in mind. Okay, fine. A ring is said to be a domain, said to be an integral domain, or in some books it's simply treated to be a domain if there does not exist non-zero elements A, B in R, both are non-zero, such that their product is 0. Okay. Simultaneously, we can say it in this way. Simultaneously, in an integral domain ID, AB is equals to 0 immediately implies either A is equal to 0 or B is equal to 0. Clear? You cannot have two non-zero elements getting multiplied to be 0. Got it? Fine. Some examples we'll see. Okay, wait a minute. Examples. Number 1, consider Z6, which was 0, 1, 2, 3, 4 and 5. Then observe that 2 times 3 is 6 mod 6. 6 mod 6 is 0. But neither 2 is 0 in Z6, that is 2 when divided by 6 doesn't give you the remainder 0, neither 3 does. So both are non-zero elements in Z6, but their product is 0. Right? So what we can conclude is that Z6 is not a domain or integral domain. We will use the term domain itself. Clear? Got it? No problem? Okay. Now observe that, so this is you can consider this to be a theorem. A ring R is a domain if and only if it satisfies the cancellation laws. That is, if RA equal to RB, then A must be equal to B. Fine, and R is non-zero. Okay, if R is equal to RB, and I should have specified this, R is equal to non-zero, then A must be equal to B. Let us see a proof of it. Proof. Suppose R is a domain. Then okay, so if R is a domain, then RA equals to RB implies RA minus RB is equals to 0, which implies R times A minus B equal to 0 by distribution, which implies A minus B is equals to 0 since R is non-zero, because it's a domain. Well, however we define domain, if product of two elements are 0, then either of them must be 0. Oh sorry, one of them must be 0. So since R is non-zero, A minus B should be 0. So this implies A must be equal to, right? Conversely, suppose cancellation law holds. Okay, then let RA be equal to 0. Okay, such that R is non-zero, A is non-zero. Fine. Then observe that then I can write RA equal to 0 as 0 times A, or let it say be written as R times 0. Fine. Since R is non-zero, A must be equal to 0 by the cancellation law, which is a contradiction. This is a symbol often used for defining contradictions, so this is a contradiction. In fact, you can also in the same way you can prove that if R is equal to 0, you can regard 0 to be written as 0 times A, and then since A is assumed to be non-zero, you will conclude that R is equal to 0. So in either case, it gives you a contradiction. Fine, not a problem. Okay, fine. The next important property which we can have in this case regarding domains is the fact that Zn is a domain if and only if n is prime. Okay, and that's a very important characterization of integral domains. So what we conclude is that, or rather what we want to conclude is that if you are given Zn and Zn is a domain, then n should be prime, and the converse must also hold true. Okay, proof. Okay, suppose n is not a prime. Then there exists A and B in Z such that both are less than n and n is equal to A times B, right? Then since n is congruent, or rather we can talk it in this way, since n is equal to 0 in Zn, the product AB must be equal to 0 in Zn, but A is non-zero in Zn, B is also non-zero in Zn, because A and B both are less than n, right? Therefore n neither divides A nor divides B, right? So A is non-zero and B is non-zero in Zn. What does this mean? So you should be pretty much acquainted with the symbols what we are using. This means that n neither divides A and neither divides B. This means that n divides AB, because obviously n will divide AB, because AB is exactly equal to n. Every element divides itself, right? Therefore this implies that Zn is not a domain. Zn is not a domain. What do we conclude from here? So taking contrapositive, Zn is a domain implies n is prime. Okay. Conversely, the converse part is pretty easy. Conversely, if n is prime, say P, let AB be equal to 0 in Zp, then that by notation implies that P divides AB, but this implies that P divides A or P divides B by Euclid's lemma, right? Introductory number theory course you should, or rather in fact introductory arithmetic course you should know this, that this holds by Euclid's lemma, that if a prime divides the product of two integers, then the prime must divide either of them, I mean one of them, right? Fine. But P divides A, this means that A is equal to 0 or B is equal to 0 in Zp, which implies that Zp is a domain. Zp is a domain. Fine. Clear? Okay. Now a slight definition I had missed, I should write it here. Definition: S, a non-empty subset of R, which we denote as S, is said to be a subring of R if S is a ring in itself with respect to the same operations as that of R. The same operations as that of R. Clear? Okay. Fine. Example. Easy to observe. Z. So this will be the symbol we will be using for subring. So Z is a subring of Q. Q is a subring of R. R is a subring of C. Right? Fine. Okay. Now we have already defined the notion of a unit. Right? Okay. Let us get back to the notions of units. Observe that no element in Z except 1 and minus 1 are units. As if R is in Z minus 1 minus 1, then R multiplied with S gives you 1 if and only if S is equals to 1 upon R in usual notation of integers. But this is not in Z, we know it, right? But this is in Q, right? This is evidently in Q, right? Every element except the 0 element. Okay, no, I should mention no non-zero element. I won't be telling about these elements being non-zero because we have already said that I do not consider 0 in any case when we are talking about inverses or units, in any case, right? Because we have already explained why we do not allow division by 0 or inverses of 0, that is reciprocals of 0, fine? Okay, so whenever we will be talking about units in R, we will always talk about them in R minus 0, okay, fine. Observe that if P by Q is an element of Q such that P is non-zero, Q is obviously non-zero because we are considering elements in Q and these are the standard forms of elements in Q, then Q by P in Q is its unit. So what we can conclude is that every non-zero element in Q is a unit. And you can see that this holds in fact for R and for C as well in terms of the usual operations. Okay, they are always considered the usual operations unless specified in case of Z, Q, R or C. Got it? So definition, this is a very, very important definition. A field is a ring, obviously a commutative ring with unity, in which every non-zero element is a unit. Fine? Okay. We often define the given R is a ring. We define U of R to be the collection of all units in R. Okay. So if F is a field, and we will use this notation itself to denote fields. If F is a field, then we can observe that the collection of all units in the field is every non-zero element. The collection of the units in Z, as we said, is just 1 or minus 1. Clear? Consider again a non-trivial example. Consider the collection of all matrix X over, let's say, a field. Okay, you can choose this to be Q, R, or C, whatever. For simplicity, let us consider all real matrices, n cross n real matrices, with respect to usual matrix addition and multiplication. Then we know that A in M in R has an inverse if and only if the determinant of A is non-zero, right? So it having an inverse is equivalent to saying that it is a unit, right? Therefore, U, the collection of all units in M and R, is the collection of all such matrices in M and R such that determinant of A is non-zero. And this is a very important ring which is defined to be the general linear group of order n over R. Fine? Clear? Okay. Now, if you have studied groups, you will see that this also admits a very important group itself. If you consider the map from the general linear group to R mod 0, let's say, R except the element 0, such that, so this is a multiplicative group. You can easily observe that the collection of all real elements except the 0 element is a multiplicative group. Okay, you should already know this, such that phi takes a matrix and maps it to its determinant. Okay, then by the usual properties of determinants, we can show that phi of AB is equal to determinant of AB is equal to determinant of A times determinant of B is equals to phi A times phi B. Okay, the general linear group is a well-defined group under multiplication. Okay, so in fact phi is a group homomorphism. Okay, the unit in R minus 0 is 1, so the kernel of phi should be the collection of all those elements in the general linear group such that its determinant is 1, and this is called the simple linear group over R. By the and in fact you can also observe that this map is in fact surjective, right? Because any real number you choose, you can always construct a matrix such that let us just take an example. Say R is in R. Just choose the matrix A which has R in the first position and all the other elements in the diagonal are 1 and all the other elements are 0. The determinant of A will be R. Okay, so this is non-zero element. Fine. So therefore this map is surjective. So by the first isomorphism theorem of groups, the general linear group over R by the simple linear group over R is isomorphic to R star. R star is R minus 0. Right. Okay. Got it? So we have already considered, okay, so consider the examples of fields. Examples of fields are basically Q is a field, R is a field and C is a field in fact. Fine? Got it? Okay. The next important property which we should be talking about fields is the following. Okay, theorem. If P is a prime, then ZP is a field. Okay? Yeah. Proof. Let A be an element in ZP. Now if A is non-zero, then obviously P does not divide A by the definition of the elements in ZP, which implies that the GCD of A and P is 1. Okay, this is something which we know because we know that the factors of P are 1 and P itself. So a common factor of A and P should be 1 on P itself. Since P does not divide A, the common factor cannot be P, therefore it has to be 1, right? Okay. Yeah. Okay, fine. Yeah, okay. It's fine. Okay. See, there is a slight abuse of notation in this case because we have written the elements in ZP as all the elements which are less than P, right? 0 to P minus 1. So saying that P does not divide A actually in this case makes no sense. But this is just a slight abuse of notation to say that A can be any arbitrary integer which does not yield the remainder 0 when divided by P. You can think of A to be in that case. So rather a beautiful notation should be considered the class of A. You can consider this to be as the class of A, the collection of all elements which admits the remainder A. You can simply think of this to be in this way. Okay, or rather, if you are more confused about the notation, just simply take it as it is explained. Okay, or rather, let me write it in a slight different way. Okay, let us choose our notation itself. Let A be in ZP. Okay, now if A is non-zero, then okay, let us just abide by the notation which we use. Okay, just consider the class. Okay, if the class of A is non-zero, then A is not divisible by P. Okay, let it be in that way. Okay, then GCD of A and P is 1, as I said. Fine. Now since GCD, therefore by the GCD lemma, I get this is also called Euclid's lemma. I don't exactly remember. There exists integers, let's say S and T, such that AS plus PT is equal to 1. Okay, which implies that AS minus 1 is equals to minus PT. Right? This implies that AS is congruent to 1 mod P. Right? AS is congruent to 1 mod P because the right hand side will reduce to 0 when divided by P, and left hand side becomes AS minus 1 congruent to 1 mod P. Then by modular arithmetic, S can be reduced to any element in ZP minus 0, which implies that A admits an inverse in ZP. Clear? Okay, fine. Okay. Now this is an exercise you can take. Exercise that no element can simultaneously be a zero divisor and a unit. Okay, I haven't defined what a zero divisor is, right? So let me just explain. A non-zero element A in a ring R is said to be a zero divisor if there exists a non-zero element B in R such that AB is equal to 0. Okay, so basically using the definition of a zero divisor, an integral domain is a ring which has no zero divisors, right? Okay, fine. This is a lemma, an immediate observation that every field is a domain. Okay, and you can prove it on your own, because if not, just take it, if not, then there exists some non-zero element R in capital R such that Rs is equal to 0 for some non-zero S, right? But this implies that this non-zero element R in capital R is not a unit, which contradicts the definition of a field, because in a field every non-zero element should be a unit, right? Okay, fine, right. Okay, so this is already a 1 minute long lecture, sorry, a 1 hour long lecture. Okay, let us talk about the last thing. Okay, so we'll talk about the last thing, which is the notion of localization or the fraction field. Okay, theorem, and this is a very important theorem. We will see why is it important when we will be getting more involved in talking about polynomials. Okay, for every domain R, there exists a field R bar. No, let's just say to be FR containing R as a subring. Okay, so for every domain R, there exists a field FR containing R as a subring. Moreover, every element Q in FR has a factorization Q equal to AB inverse with A and B in R, and B is non-zero. Fine. The first thing which you should observe here is that this is exactly the same properties. If I choose that if R is Z, then your f of R should be Q. And the proof is exactly how we construct rationals from integers. Okay. So how is the proof done? Consider an element AB in R cross R and define a relation tilde on R cross R by, so we say that AB is equivalent to CD if and only if AD is equals to BC. You can check that this is an equivalence relation. Okay. Let the class of AB under this equivalence relation, okay, be denoted as A by B. Okay. Let FR be the collection of all these equivalence classes such that A is in R, B is in R minus 0. Okay. Okay, I should have mentioned it previously. I should take this to be from here. Okay, fine. Or rather simply, yeah, okay, fine. For a simpler notation, let me just choose R cross R such that B is non-zero. Okay, here we also have the second element of the order pair to be non-zero. Okay, so having this, define operations on FR as A by B plus C by D to be AD plus BC by BD, and A by B times C by D as AC by BD. Okay, then these are eminently well-defined operations. Just choose two representatives of these elements. Let us choose A prime and B prime, and so so what I'm trying to say is that just choose A by B is equals to A prime by B prime, choose C by D is equals to C prime by D prime, then prove that if A by B plus C by D is equals to equal to AD plus BC by BD, then A prime by B prime plus C prime by D prime should also be the same. Just verify it. Okay, fine. In fact, every non-zero element in FR is a unit, as if I choose the element A by B from FR such that A is non-zero, because we defined 0 by 1 to be 0 in FR. So this is constituting as the 0 element, and 1 by 1 in FR as the unity element rather. Okay, so if A by B is in FR such that A is non-zero, then B by A is its unit. Okay, and if you choose any element Q from FR, then there exists some A in R, non-zero B in R, such that Q is of the form A by B, or a simple notation A B inverse. Also, R is contained in FR as a subring, choosing A in R as the equivalence class A by 1, nothing else. Clear? Okay. So this FR for a given ring R, for a given domain R, given R a domain, F of R is called its fraction field. Is called its fraction field. Clear? Okay. An important notation in this case, consider a field, consider a ring, consider a domain. Okay. So this is an exercise first. You can a very easy verification. Let K be a domain, then Kx is a domain. Okay. Let me just prove it in a very simple way. Okay. So let fx equal to a0 plus a1x and so on till a(x to the power n), and gx equal to b0 plus b1x and so on till bn(x to the power n). Okay. So let this be, both of them be non-zero elements, not identically zero functions. That is, not every coefficient is zero. At least a0 and b0 are non-zero, right? At least a0 and b0 is non-zero. Fine. Okay. In kx, then how do we define fx gx? This is defined to be a0 b0 plus anything. We are not concerned about that. Okay. This can never be equal to 0, as then a0 b0 must be equal to 0, while neither a0 is assumed to be 0 nor b0 is assumed to be 0. Fine. And if you're not satisfied with this, if you think that okay, a0 and b0 can be 0, a0 or b0 can be 0, but some other coefficient might be non-zero, then you will have the same trick for that as well. Okay, you will have the same trick for that as well. Okay, choose any arbitrary coefficient which is non-zero and check the same domain properties for that, right? Because, or you can say it in a more familiar way in this way. Okay, so let us remove all these. Okay, a better way of writing the proof is the following. Because when I'm lecturing on these things, there is no note in front of me, so these are all just just thoughts coming in my mind whenever I'm speaking. So suppose fx gx is 0, right? Then that implies every coefficient of fx gx must be 0. Okay, I did a mistake here. I'm extremely sorry. I was not concerned about the coefficients a0 and b0. I was concerned about the coefficients a and bn. I'm extremely sorry. Okay, because whenever we are defining polynomials for the well-definedness of a degree, that is to be xm, whatever, doesn't matter. Okay, so I will automatically have an to be non-zero and bm to be non-zero, right? But that implies that an bm must be 0, which would imply that either an is 0 or bm is 0, as R is a domain. Right? While this is a contradiction, because we have an is non-zero and bm is non-zero, right? Therefore, the if k is a domain, so kx will also be a domain. Fine. So let k be a domain, then kx is a domain. So we can talk about its fraction field. So we define f of kx to be the collection of all polynomials of the form px by qx, such that px, qx are coming from kx, qx is not identically 0, and this is defined as k round bracket x, and it's called the field. So it's a field. So it's called the field of rational functions. It's called the field of rational functions. Sorry, rational polynomials over k. Yeah, got it. Fine. I would end this lecture by explaining something and then giving an exercise. Okay, let k be a ring and uk be its collection of units. Then observe that if a and b is in uk, then there exists element s and r in k such that both are non-zero, because obviously we are concerned about elements in k which are units, so they are automatically non-zero, such that a is equal to 1 and br is equal to 1. But observe that then ab times r is equals to a times br is equal to a. So if I do it ab times rs, so you have a s here, so you have a s here, so it's equals to 1. There, that implies that ab, okay, fine, that implies that ab, so ab is in uk, right? ab is in uk. Fine. You can obviously check one thing, that ab cannot be 0 and rs also cannot be 0. Fine. Just use what I said, that an element cannot be simultaneously a unit and a zero divisor, because if r is a unit, so it cannot be a zero divisor, right? See, if a is a unit with respect to r or s, whatever, then that is also a unit with respect to a. Fine, right? So r cannot be a zero divisor, neither a can be a zero divisor, so this is not possible, right? That is why we could have done this. We can't do this. In fact, now 1 itself will always be a unit, right? It is obviously a unit. Therefore, okay, I mentioned it as k, right? Therefore, the units over any ring is a group, is a multiplicative group in R. Okay, this is called the group of units. Of R. Okay, fine. Now the exercise I would want to give is that if A is in Z, then the class of A in Zn is a unit if and only if A and N are co-prime. Once you prove this, you can conclude that the cardinality of the group of units of UZn group of units of Zn is exactly equal to the number of elements which are co-prime to n, so that should be phi n, where phi is the Euler's quotient function. Clear? Fine. So let's end this lecture itself here. In the next lecture, we will talk about some more aspects of these things, and then we will be moving on to the notions of homomorphisms and ideals. Okay? So meet you guys in the next lecture.